in the last lecture, the idea that we talked about was working in spherical and cylindrical coordinates. And we talked about, how every integral has the various pieces. And we said, there's this part where you break stuff up. And you have to sometimes add extra terms. Now, we've seen this in a couple of cases. So when we switch from Cartesian coordinates to polar coordinates, we said, well, dy dx is r dr d theta. And we said, well, similarly, if you go from Cartesian coordinates in 3 dimensions to cylindrical coordinates, there's again that r showing up, r dz dr d theta. And of course, our big one from last time, if we switch from Cartesian coordinates to spherical coordinates, we got our rho sine of phi, d rho d phi d theta. So that rho squared sine phi. So in some sense, we have like these extra pieces showing up, and we'd like to understand how do we figure out what goes there? What goes inside these boxes? Now, we were talking about change of coordinate system, but really, in essence, what's happening when you're talking about changing your coordinate system, it's also talking about changing your variables. And so if you go back to Calc 1, a long time ago, we talked about integration using substitution. And we had the following. It said if I want to integrate a to b of f of x dx, I can integrate from appropriate bounds f of g of u times g prime of u du. Well, normally we talk about going from the complicated part to the less complicated part. But the point here is that this g prime of u actually had an important purpose. Now, sometimes we say, oh, it came out of the chain rule. But if we think about it in terms of integration, it also is telling us something about the behavior. And we're going to talk a little bit more about where it's coming from. So you might say, aha, so somehow there's a derivative involved in those terms. And the answer is kind of, not far off. All right, well, so our goal for today is to figure out where do these come from and how can we apply this to more general settings. In essence, what we're trying to do is substitution for multivariable integrations. How do you carry out that substitution? Or if you don't like substitution, you can call it change of variables, you can call it change your coordinate system, but that's what we're getting to. Well, how do we begin? So what we're doing here is we want to go between 2 different coordinate systems. So here I have a very, hopefully relatively simple example. I'm not explicitly telling you what the change is, but I'm going from a coordinate system where I have u and v to a coordinate system where I have x and y. And what happens is every single point in u and v corresponds to a point in x, y. So I've mapped my space. And here, this corner, which is marked with a dot, maps to that corner. You'll also notice that there's these grid lines here. Well, they become somewhat more interesting grid lines over there. So we're transforming from one space to another space. And we can think about, well, what's happening with integration? The idea of integration is pretty straightforward. We start by saying, let's take our region and let's break it into little pieces. So I can take my region here in the UV plane. It's nice and square, so I can break things up. And okay, there's a little piece. Integration says, what happens on that little piece? And you say, well, it's about that. And now I'll add them all up. Well, of course, what happens is this little piece translates into a little piece in the xy setting. And so now our goal is, well, okay, what is that little piece? How do we understand it? And what can we do about it? So the way to understand it is just think about what the pictures are. If we think about it, what do I need to know? I really need to know how big is that little tiny rectangle. Well, rectangles are easy. The problem is that's not going to be a rectangle. So, no surprise, we're going to approximate. So here, on the first piece, this is the rectangle back in the UV setting. And it's very simple to approximate. I just say, if I want to know what the area here, change in U, change in V, multiply them together, life is good. Now, what's this middle part? Well, this middle part is the result of what happens if I translate over. So now, the original one, that was in the UV plane. Here, I'm in the XY plane. And you'll notice it's actually not quite squared. So there's a little bit of turn to it. So now, the question is, what do you do about the area? And conveniently enough, they actually give us the answer right away. So we're not going to be left in suspense. We'll say, you know, if you look at things close up, even though it's not perfectly square, it's almost perfectly square. Or really more accurately, it's almost like a nice parallelogram. So what we can do is we can say, let's approximate this area with a parallelogram. So if we can figure out what that area of the parallelogram is, now we have an approach. We can say, aha, break our new space up into tiny little pieces, and then we can now say, I know what the area of each little piece is, and we're ready to go. We're ready to do integration. So how do we go about finding the sides of the parallelogram? Well, in essence, you can think about what the picture here is saying. So I have here one side, and let's say this corner, what would that corner map to? Well, let's say it maps to this corner. Okay, so suppose I know that those corners map. If I want to know what happens to this side, well, here I am. I'm in the setting where x is a function of u and v. So remember, this here is in the uv plane. And over here, we're in the xy plane. And I say, all right, I know how x depends on u and v. And I know how y depends on u and v. So if I think about what happens, if I'm going to perturb in the u direction, what will happen is I'm going to perturb on one side of the parallelogram. Well, how much? Well, the answer is if I want to know how much I changed in the x direction, I'm going to change, running out of space here, I'm going to change x sub u delta u, comma, y sub u delta u. What's happening here? Well, it's a vector, and what I'm doing is I'm decomposing my change. And to understand, I say, well, look, x depends on u and v. So if I want to know how much x changed as I change u, I say, well, what's the rate of change with x with respect to u? That's the partial derivative x sub u. What's the amount of change of u? Well, that's the change in u. That's delta u. So it's the rate of change in the u direction times the amount of change of u. Similarly, I do the same thing in y. How does y change as I change u? And again, I'm focusing in the y direction, times the amount of change of u. If I combine that together, that tells me that this vector is going to translate over here to give us an approximation. And similarly, if you do the other side. So we get the following. The sides of the parallelogram are given by partial derivatives times our changes. So partial x, partial u times change in u, partial y, partial u times change in u. Again, you have to imagine the side that corresponds to change in u, what happened to it. Then there's a side that corresponds to change in v, and then what happens to that? Well, if I change v, I'm going to change both the x and the y entries. So I get a vector. Now, how do I find area? Well, what's the answer? How do you find area of parallelograms? Cross product. Well, there's one catch. What's wrong? What? It's 2D. Cross product, you need 3D. How do we fix that? Yeah, zeros. Okay. So we just say, look, 2D sits in 3D. You just toss the 0 on the end. So now we have two nice three-dimensional vectors. We can take the cross product and we work it out. Well, if you work it out, it turns out that what you get is the following. you're going to end up with a determinant of a 2 by 2 matrix. And the entries of that 2 by 2 matrix are the partial derivatives. So partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v. The delta u and delta v, you'll notice that you can pull them out. Because if you look here, in the first vector, all the terms have a delta u. So you can pull that out. That's a common term. In the second vector, everything has a delta v. You can pull that out. Again, that's a common term. Now, one thing I want to be careful of, and this notation is not the best at saying this, is when I talk about the determinant, it's not just the determinant. That determinant helps find the cross product. It finds an entry in the cross product. It's the absolute value of the determinant. So better notation would have been to put even another set of bars here. So the absolute value of this 2 by 2 determinant. But I hope you will forgive me if I don't keep writing both set of bars. Now, this has a name. It's called the Jacobian, and named after a mathematician. And hence, that's why it's capitalized. And what is it measuring? Well, in essence, if you think about the picture we started with is, well, let's put the picture back up here for a second. If you look at the picture we started with, you can actually just eyeball these and say, hold on, it changed size. So it not just changed shape, but one of them is definitely smaller. This is definitely smaller than that. And that's not just a trick of the light. It actually did shrink. So what's happening is that Jacobian is trying to capture information. How much did you shrink or expand? Now, if we're trying to sound fancy, we use words like dilation or contraction. But it's all about how did your size change? How is that little piece changing in size? Now, a couple of pieces of advice about the Jacobian. It's a very forgiving matrix in the following sense. We don't really care about the sign. And so if you forget which variables go where, so you might say, okay, is it the x, then the y, or is it the y, then the x? You'll still get the same value. And one of the things you might notice, and it's kind of convenient if you can spot certain patterns, notice as we go down, we have the same variable in the numerator. So x, x. Then in the next column, y, y. Where if we go across, we're going to have the same in the denominator. So u, u, v, v. And so if you can't remember how to do it, just say, okay, look, I have all my variables in one setting. Those are going to be in my rows. All my variables in the other setting, those will be my columns. And even if you do what's called a transposition, so maybe say, oh, what, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, you're still going to get the same thing. See, it's a very forgiving. So just remember, it's all the partial derivatives put together, take the determinant, and make sure it's positive. And that's it. Okay. Well, we should do something. Let's do an example. So given a change of coordinates, and here's our change of coordinates, x is r cosine theta, and y is r sine theta, find the Jacobian of r and theta. Well, let's see what that would be. So, what do we want? We want to take the derivatives of our old variables, which are x and y. So I'm going to take derivative of x, derivative of y, derivative of x, derivative of y, with respect to the new variables. So we'll have partial r, partial theta, partial theta. I'm going to form that 2 by 2 matrix. I'm going to take the determinant, and then I'm just going to make sure I get a positive answer out. So, what's the derivative of x with respect to r? Cosine theta. What's the derivative of y with respect to r? Sine theta. All right. Next we'll come down. What's the derivative of x with respect to theta? Minus r sine theta. What's the derivative of y with respect to theta? R cosine theta. So now we take our determinant, 2 by 2. So we multiply down the diagonal. that would be r cosine squared theta. Now you multiply on the anti-diagonal and you subtract. So minus r sine squared theta. Well, two wrongs make a right. So minus minus. The r factors out. Comes cosine squared theta plus sine squared theta. And do we simplify any further? Yeah. Cosine squared plus sine squared is 1. So our final answer is r. Now you might say, hey, this sounds really familiar. And it is really familiar. Where is that r coming from? It's polar. See, that's when we changed coordinates from Cartesian to polar. We said we needed an r. So that r and this r are related. In fact, they're the same r. Now there's one note here I should point out. This is a very useful fact. It says, suppose I'm jumping back and forth between coordinate systems. So I can talk about a Jacobian going from the xy coordinates to the uv coordinates, but I can also talk about Jacobian going from the uv coordinates to the xy coordinates. So picture-wise, we have this idea of I can jump back and forth. Well, so I have a Jacobian that will go in one direction. That would be, let's see, this would be Jacobian of, I believe, xy, and they have Jacobian going in another direction, Jacobian uv. If I multiply them together, the result is 1. Now, why is that? Well, if I do the map where I jump back and forth, I get to where I started. So what's the total change? How much have I dilated or contracted? Well, I haven't. I'm still the same. So because I haven't expanded, I haven't contracted, it means the result of doing it twice is 1. And these are just saying what's the result of the individual maps. And to get the net result, you multiply. So this is a way to save a little bit of work sometimes. And we are definitely all about saving a little bit of work. All right. Now, how do we go about doing our change of variable? Here's the idea. We should probably do the slow reveal. So I have my region S in the UV plane, and I have my region R in the XY plane. And our goal is to figure out what do I do when I want to transform an integral. Instead of saying x and y, I want to get an interval in terms of u and v. Now, the key observation is to say that the Jacobian has given us information. Namely, it says, if I have a little piece here, I can now say the size of that little piece over there. And of course, you might say, but you can only say an approximation, but that's okay. Integration is all about approximation. So it's okay if it's just an approximation. The key is it gets better the smaller you get. So here we begin. We say, well, look, if I wanted to integrate over my original region R, which is the one that looks complicated, well, you do what you do with integration. You break things up into parts, usually in 2 directions, and you have the contribution from each piece and the size of each piece. Well, that's, of course, depends on how I break things up. So here's an idea. Let's be smart, and of course, it depends what you mean by smart, and say, I'm going to choose the way to break up R. So instead of breaking R up into little tiny squares or little tiny rectangles, I'm going to break R up according to what S tells me to do. So in other words, I say, come over here, break S up into pieces, and then each one of these pieces maps over into a piece in R. So this little piece maps to that little piece. And that's how I'm going to break my region R into parts. And now I say, okay, if I want to know the contribution from here, well, there's a few things I need to know. I need to know the value of the function. To figure that out, I say, well, let me figure out where a point that mapped over. So this is, I look at a point that mapped over, and I evaluate the function. Then I need to know the size, and that comes from using that Jacobian. And then I'm adding up over all the rectangles. And now we just say, hey, this sum is really just an integral over my original region S of the function where I've changed my variables So now it depends on u and v. So x is a function of u and v, y is a function of u and v, meaning our whole function depends on u and v. And we have our Jacobian term showing up. And so that's it. That's the idea. So we can now say if you want to do your change of variables, so switching from an integral with respect to two variables, it can be x and y, it can be anything, to a set of new variables, let's say u and v, well, you do what you expect. You look at your bounds, you update your functions to be in terms of your new variable, and then you remember that you have to keep track of how things break up. And to do that, that's where the Jacobian comes into play. So that's why we wanted to introduce the Jacobian. So in general, how do you go about doing a change of variable problem? Well, it's pretty straightforward once you understand how integrals work. So it's almost a very short process. Now, what's the first step? It's to identify the substitution to make. So I have an integral. I need to figure out what substitutions to make. What can you look for? Well, you can look for functions that are on the inside, because that's one place where substitution makes sense. You can also say, I have some really strange boundary curves, so maybe I should change that. But there's a third thing that you should look for, which I think is very applicable in the short term, which is to say the problem might tell you. So if the problem tells you something, you should probably do that. And I will say, at this point in time, any problem that you see that involves change of variables in this class, we will tell you what the change of variables is, because it is subtle. It is not an easy thing to do, and it takes a lot of practice. And I know there's already a lot for us to practice. But this is in the future, when you go about and become professional change of variable people. And if you need to do that, here's what you do. Occasionally, it can be useful to say, I know what substitutions to make. In other words, I know what u should be in terms of x and y, and I know what v should be in terms of x and y. It can be useful to say, well, what about going the other direction? If I have a u and v, can I figure out what x and y are? Now, you don't need to do that. But it can be helpful, and if you get stuck, that might be one way to help you get unstuck. So that's the first step, identify the right substitution. But again, most of the time, I think that translates into 100% of the time, when we ask you, it is just read off what we tell you to do. The second step is really broken into three parts. And I wanted to break it into three parts to emphasize these are three different pieces of the integral, and each one is more or less independent. So I didn't want to label these 2, 3, 4. I want to say, well, look, now you have the three parts. Do them in whichever order you like, because they will more or less be free of each other. That being said, do the Jacobian first. The Jacobian will have a slight impact on how you rewrite the function. We'll go through and point that out as we go along. But they can be essentially done independently. So find the Jacobian. In other words, how do you break things up? Find how to rewrite your function. And finally, what are your new bounds? Now, I think the new bounds is oftentimes part of the hardest thing about these change of variables. Because it's not just a simple matter of like, oh, it's new numbers, like we had in Calc 1. We have to figure out what are the new curves. So here's what I like to do, is I say, okay, let me take my old region, and let me look at the figure. Let me see the shape. And I'm going to write down every single bounding curve. And I write down what the equation is in terms of my original variable, so maybe in terms of x and y. And now I say, let me rewrite these same equations, but all in terms of u and v. Those new equations become my new boundary curves in the new variables. And I make my new figure. And then I set the bounds. So that's how I recommend doing the bounds. And once you have all these three parts, how you split things up, how you write the function, what your bounds are, put everything together, and you've done your change of variable. So it's time for us to do an example, maybe two examples. We'll see how far we get. So find the integral from 0 to 1, integral from x squared plus x to x squared plus 1 of 6x divided by 1 plus in the quantity 1 plus y minus x squared cubed dy dx by doing a change of variables. Oh, that's good. We just talked about that, so we know how to do that. Where u is y minus x squared and v is x. So the good news is step 1 is given to us. All right, good. So we know what our substitution is. Now let's go through and work through our various pieces. So let's start with the Jacobian. So I'm going to say, I'm going to compute not the Jacobian of u and v, I'm going to compute the Jacobian of x, y. And what do I mean by that? Well, I'm going to come here, and I'm going to just start with u and v as given. And I'm going to take those partial derivatives. So I'm going to take the determinant of, and again, if you forget, you're okay. The Jacobian is very forgiving. So partial u partial x, partial v partial x, partial u partial y, partial v partial y. All right, what is partial u partial x? Minus 2x. What is partial v partial x? 1. Partial u partial y? 1. Well, that was really easy. Okay. Partial v partial y? 0. So we take the Jacobian, and lo and behold, out comes -1. But we take the absolute value, and so we really get +1. Well, that's very convenient. Now, don't get lulled into a, oh, it's 1, it'll always be 1. No, no. It doesn't always have to be 1. It could be something more interesting, as we'll see in a few minutes, if time allows. Okay, so we now know the Jacobian, which also, by the way, I know that the Jacobian of xy times the Jacobian uv is 1, so this tells me that the Jacobian uv is also 1. All right, what's the next thing for us to tackle? We've done our Jacobian, how we broke things up, and we said, oh, Jacobian is 1, good. Don't have to worry about any correcting terms for dilation. What's the next thing? Or what's a next thing? Change the bounds? Okay, let's talk about the bounds. So if we're talking about the bounds, let's think about what's happening here. Where does x go between? X goes between 0 and 1. So I have 0 less than or equal to x less than or equal to 1. Now where does y go between? Well, x squared plus x, that's less than or equal to y, that's less than or equal to x squared plus 1. Now x squared plus 1 is a parabola that's been shifted up by 1. So that one's pretty easy to draw. So I come up here to 1, and I'm going to have a parabola going up, and here is 2. Sorry, here's 1, or I meant 2. 2 is over here. All right, so that's that parabola. What about x squared plus x? What does that look like? Well, what's the basic shape? Yeah, it's a parabola. Yes?
I was going to say, wouldn't it still be a parabola, but centered at 0?
Well, it'll be a parabola. If you go through and do completing the square, you'll see it's actually centered at -1/2, comma, -1/4. But I don't need to know that much. For me, I can say, what happens at 0? It's 0. What happens at 1? It's 2. So it's a parabola that goes from 0, 0 to 1, 2. Okay, so it's doing something like that. It will actually dip down below, but I don't care about that part because I only care about what happens for x lying between 0 and 1. Meaning, that's my region. Now that's the region according to x and y. Let's talk about our 3 bounding curves, because there are only 3 curves that bound this. What are my 3 bounding curves? Well, the y-axis is a bounding curve. How do I write the y-axis? X equals 0. What else is a bounding curve? The parabola, y equals x squared plus 1. What else is a bounding curve? Y equals x squared plus x. These are all bounding curves. Now, what we want to do is we want to say, okay, I want to translate these equations in terms of u and v. Now, some of them are pretty easy. For example, x equals 0. Given that I know x equals 0, is there a simple way to write that in terms of u and v? V equals 0. Okay, well that's good. Now what about y equals x squared plus 1? Another way you can write that is as y minus x squared equals 1. The reason I do that is I see a y minus x squared. So what does that become in terms of my variables u and v? U equals 1. Now I come to y equals x squared plus x. How can I write that? Y minus x squared equals x, which becomes u equals v. Now those are nice bounds. No more curved lines. So let's see if we can draw that. So this is in the x, y plane originally. We're switching to the u, v plane. So we have v equals 0. So v equals 0. That would be here along the u-axis. So here's v equals 0. And then we have u equals 1, which would be here. U equals 1. And then we have u equals v, which is there. U equals v. And then we say, okay, well, what's our region? Well, it's the piece that's bounded. So there's our region. All right. So those are our bounds. There's something else that has to be done to finish up. So we've talked about the Jacobian. We updated our bounds. Or at least we've updated our region. We'll get our full bounds in just a moment. The last piece, the function, the equation. So how can I rewrite 6x over 1 plus y minus x squared cubed? Yeah, so I can rewrite 6x over 1 plus y minus x squared cubed becomes 6v over 1 plus u cubed. All right. This looks promising. Let's put it all together. So our new integral will be the following. It's going to be an integral 6v over 1 plus u cubed. And now the Jacobian is 1, so times 1, which is our Jacobian, times something. All right, what's our something? Well, we have to make a choice. Is it better for us to do a vertical slicing or a horizontal slicing? Vertical. Now you probably picked up on that because I actually drew the vertical, but I didn't draw the horizontal. So you must be like, it must be vertical. Now, you might say, why? Why are you doing it in that order? Well, if you do vertical slicing, what's the order of integration? It would be dv du. Now, you'll notice integral with respect to v, not so bad. Integral with respect to u, not so fun. It's possible. I did it once in a Calc 2 class. It took us about 40 minutes, but it can be done with the tools that you have. But we don't want to spend 40 minutes because we like ourselves. But there's another reason why the dv du is good. And let's point that out now. Okay, where does u go from? 0 to 1. And where does v go from? 0 up to the line, v equals u, so 0 to u. Now, here's the other reason why it's good to slice vertically. You see that 0 there? If you were slicing horizontally, it would not be a 0. 0 is your friend. As often as possible, try to get 0 in there. And so given a choice, try to put 0 in. All right, well, let's do the integral. If I integrate 6v with respect to v, what do we get? 3v squared, or 1 plus u cubed, evaluated from v equals 0 to v equals u, du. We evaluate that, we get the integral 0 to 1 of 3u squared over 1 plus u cubed du. And how can we evaluate that? Or do we know how to integrate that? We can do a u sub. Well, of course, it's weird to say a u sub when our variable is already u, but we can do substitution. And this one is probably one you might be able to do in your head. Because if you say, look at the derivative of the denominator, derivative of 1 plus u cubed, that's 3u squared. That's the numerator. So whenever you have that, what do you think of? Natural log. Natural log of 1 plus u cubed, evaluated from 0 to 1. And you evaluate, plug in 1, you get natural log of 1 plus 1, known as natural log of 2. Plug in 0, you get natural log of 1 plus 0, which is natural log of 1, which is 0. And so there's our answer. Natural log of 2. Good. Good. Easy. Easy. All right. Good warm-up. Let's try something a little more interesting. So, by substituting u equals x squared plus y and v equals x squared minus y, find the following. So we're taking the integral 0 to 1, integral negative x squared to x squared of a crazy expression, dy dx, plus another crazy integral from 1 to root 2 of really, well, okay, we're doing stuff. We're definitely doing stuff here. Okay. Well, we know the substitution. Step 1, done. Here we go. I feel good. I've made progress. I figured out what substitution to make. All right. Well, that's probably not enough progress to get the final answer. What do we do next? What's an option of what we can do next? Jacobian. I think the Jacobian is a good thing to do early. So I'm going to compute the Jacobian. So Jacobian of x, y. So that's going to be the determinant of, and I'm probably going to write down something different than what I wrote down last time, but that's okay. So I'm taking, these are my new variables, u and v. I'm going to take the derivatives with respect to x and y. So I could take, for example, u sub x, and I could take v sub x, u sub y, v sub y. All right, so I'm going to take, that's my Jacobian. I'm going to take the determinant, make sure I'm positive. So, in our case here, what is u sub x? 2x. What is v sub x? 2x. Whoop, I said v sub x, but I put it in the wrong place. There, v sub x, all right. Okay, what is u sub y? 1. What is v sub y? Negative 1. Okay, we take the determinant of this. We're going to get 2x, well, minus 2x. 2x times negative 1. Subtract 1 times 2x, which is 2x, which is minus 4x. But of course, I want the positive, because the Jacobian should always be positive. Because the reason it should be positive, it's a measure of how big you're contracting or dilation, which is a positive quantity. So I get rid of the negative, which tells me that my Jacobian of xy is 4x. Now, what does that say? Well, here's the thing. It's not 1, so we actually have to think a little bit. But that's all right. We're good at thinking. What this tells us is that if I want to look at du, dv, it's the Jacobian of xy, dx dy, or dy dx. Doesn't really matter. But in our case, that's 4x dx dy. Now let's look at our integral. Notice I have a 4x dy dx. So that these pieces here will become my du dv or my dv du. I don't know yet. I don't know the integral order of integration. But when I do my substitution, that 4x dy dx will become what I need it to be. So one of the things that tells me is when I'm looking at the function and I'm saying, oh, let me rewrite the function, I leave the 4x alone. My function now, the part that I care about, is the rest of it. That's the part I care about. The e to the x squared minus y over 1 plus x squared plus y squared squared. And I should stop writing in pen. That doesn't show up on the screen. Okay. So that, when I talk about changing the function, it's the other stuff that's not going to be rolled up into the Jacobian. Okay. What's the next thing you want to talk about? Maybe let's do the function, since I just talked about changing the function. All right. So the e to the x squared minus y, what will that become? E to the v. 1 plus quantity x squared plus y squared becomes 1 plus u squared. So that looks like a pretty nice function. I mean, these are the kinds of functions we like. They're definitely much nicer than what we started with. Okay, so there's our function. We know how to handle the Jacobian part. What's left? The bounds. Oh yes, in this one we're going to have some interesting bounds here. So let's talk about our bounds. We're going to go from 0 up to 1. And what happens? Well, we have some curves. We have on the top y equals x squared, which is going up. And we're going to intersect here at 1. And on the bottom we have y equals minus x squared, which is going down. So y equals x squared, y equals negative x squared. So I'm finding this shape here. All right, but we're not done yet because that's just the first integral. The second integral says go out a little bit further. Now we go out to root 2, 1 to root 2. The top, it's the parabola 2 minus x squared. Now what does 2 minus x squared look like? It's an upside down parabola. It would start at 2 and start going down. Well, by great coincidence or design, it passes through 1, 1, and it hits 0 when my y value is 0 when x equals square root of 2. So it's coming down, and I'm going to see this. So this is y equals 2 minus x squared. X squared minus 2 is doing the same thing, but it's a parabola going up, starting at negative 2 is my intercept, moving up, hits, and goes up. So this is y equals x squared minus 2. And so now the second integral finds that. So we could try to do each integral separately, but I suspect it might be better to do them together. Their powers combined, they may make an easier problem. So let's talk about our curves. We have 4 bounding curves. Y equals x squared. Y equals negative x squared. Y equals 2 minus x squared. Y equals x squared minus 2. Let's go through each one. What's a better way to write y equals x squared so that we can get it in terms of u and v? X squared minus y equals 0. So again, I'm just rewriting my boundary curves. I'm just rewriting it to set myself up for success. And success here says, how can I get it in terms of my new variables? What's a better way to write y equals x squared? X squared plus y equals 0. How about y equals 2 minus x squared? X squared plus y equals 2. Y equals x squared minus 2. What's a better way to write that? X squared minus y equals 2. Now, we've written these in these particular way because these now become nice in our new coordinate system. X squared minus y equals 0 will become v equals 0. X squared plus y equals 0? U equals 0. X squared plus y equals 2? U equals 2. X squared minus y equals 2? V equals 2. Which means if you go and now sketch your coordinates in the u, v plane. So over here, this shape, kind of interesting shape, but hard to navigate, that was in the xy plane. In the uv plane, we have ourselves a very nice shape. It's a nice box. And really, looking at the function to integrate, there's no motivation to do one over the other. So let's just say our integral 0 to 2, 0 to 2, e to the v, 1 plus u squared, that's our function. The 4x combines with the dy dx to become dv du or du dv, doesn't really matter. And notice that this is one of those functions that now we can actually pull it apart. 0 to 2 e to the v dv and 0 to 2 1 over 1 plus u squared du. What's the integral of e to the v? E to the v. Then we're going to evaluate from 0 to 2. We'll come back and do that in a second. What's the integral of 1 over 1 plus u squared? Arctangent of u. It's been a while since we've seen you, arctangent. Hope you're doing well. All right. So, e to the v evaluated from 2 to 0 will give us e squared minus 1. Arctangent of u evaluated from 2 to 0 will give us arctangent of 2, and of course we subtract arctangent of 0, but that is 0. Which means our final answer to what looked like a very hard problem was not so hard. Once we did that change of variables, things got simpler. Well, that's why you do change of variables. You always want things to get simpler. You don't take a calculus class because you want complicated stuff. Now, we've talked about dimension 2. What about dimension 3? Okay. The answer is it works very similar. But now, instead of having a 2 by 2 determinant for your Jacobian, 3 by 3. And so, why does that? Well, determinants turn out for 2 by 2 determinants are finding area. For 3 by 3 they find volume. That's one of the things that we did a long time ago in the classroom, no, actually it was in here we did that. That we talked about the determinant finds volume. Now, we're going to not delve into this. We just want you to know it's possible. But we're not going to actually ask you to carry it out because it takes a long time and it's subtle. But I want you to know it's possible. And in the moment I have left, well, I have a few minutes left, suppose I wanted to switch coordinate systems. So I have x, y, and z, that's my coordinate system, and I currently have, and I'm switching to rho, phi, and theta. I want to say, well, what's that Jacobian turn out to be? Well, if you work it out, so the Jacobian, rho, phi, theta, is a 3 by 3 determinant. So that would be what? Well, you take x rho, y rho, z rho, x phi, y phi, z phi, and x theta, y theta, z theta. So those are your determinants. So if you work this out, x with respect to rho, that's sine phi cosine theta. Y with respect to rho, that's sine phi sine theta. And z with respect to rho is cosine of phi. Then you come down, take it with respect to phi. You get rho cosine phi cosine theta. Then you get rho cosine phi sine theta. And then you get minus rho sine phi. And then you take it with respect to theta, you get minus rho sine phi sine theta. And then you get rho sine phi cosine theta. And then you get 0, because there's no theta. And you do some math stuff, and it turns out you get rho squared sine of phi. So if you wondered, where does the rho squared sine phi come from? Right there, right there. Now, if you don't check, to believe me, do the math stuff. All right, maybe a little bit more practice would be good. So let's try this one. This comes from a recent exam. Evaluate the integral from 1 to 2, integral 0 to 2 minus y, of 2y cosine x plus y cubed minus 3 times x plus y dx dy by setting u equal x plus y and v equals y squared. Now, one of the things that's interesting about this integral is, let's look at these bounds here. The initial bounds, what do they look like? Well, what do we have? We have that y is going from 1 to 2, so here's 1 to 2. and then x is going from 0 to the line x equals 2 minus y. Well, the line x equals 2 minus y is a line that goes down. And so what you have is that your initial region is actually already a pretty great shape. This is a very nice shape. And it's kind of unusual to say, let's switch. Because oftentimes we switch and we do substitution, we have a really strange shape for our region. Okay, well, maybe it'll be useful to switch. Now looking at it, it seems like it'll be very useful to switch because we can see we'd have a hard time integrating with respect to x. We have an x cubed on the inside, and there's nothing on the outside to help us. But we even have a hard time integrating with respect to y, because notice there's a y cubed on the inside. That 2y, that's not enough to help us. So whether we integrate first with respect to x or with respect to y, in both cases, we're in trouble. Well, that's normally, but look, it says do it by making a choice, by setting something. See, really this is a change of variable problem. So we're going to carry out our change of variables. All right, well, let's go ahead and get started. Probably the first thing we should do is identify the variables. Well, okay, no, that's done. All right. The next thing, let's talk about our Jacobian. So I'm going to compute the Jacobian. And the Jacobian x, y. It's going to be functions of x and y. And so what will this be? Well, it's going to be the derivative u sub x, v sub x, u sub y, v sub y. Take that determinant. U sub x is 1. V sub x, 0. Well, that's convenient. U sub y is 1. And v sub y is 2y, which says our Jacobian xy is 2y. Now what does that tell us? Well, what it tells us is it says the following, that du dv is equal to the Jacobian xy dx dy, or 2y dx dy. You'll notice we have a 2y dx dy. So that part of the integral goes into the change, into the area dilation part. All right, so that's the Jacobian. Now, what's the next thing? Well, let's talk about our function. Now here, it's pretty easy, because there are no y squares. Everything looks like x plus y. The 2y, again, that's not going to be part of our function. So we're going to get cosine of u cubed minus 3u. Okay, well, that's interesting. Now, we have to tackle the final part, the final piece. We've talked about how we break pieces up, and with Jacobian, we talked about what our new function will be. Now we're going to talk about our bounds. So let's go through and figure out our bounds. So the way I like to do it is write down the old bounds. So we have 3 curves, because it's a triangle here. So this right here, this bottom part, that's the bound y equals 1. The left-hand side, what's that? Well, that is x equals 0. And now this other side, well, that comes from our x equals 2 minus y. Now, we'll rewrite that, of course. What's a better way to write that? Looking ahead, x plus y is really clean. So we'll say our 3 bounds are x plus y equals 2, x equals 0, and y equals 1. Now, x plus y equals 2. I see that x plus y is u, so that's u equals 2. Y equals 1. Well, I can see v is y squared. So if y is 1, that says that v is 1. You probably noticed I skipped over 1. Okay, x equals 0. Now notice there's not really one of these that has an x in it. So let's suppose I know that x equals 0. What I can conclude is that u is equal to y, and I can conclude that v equals y squared. Well, wait a second. We just said u equals y. So if v equals y squared, v is also equal to u squared. So there's the other curve. So now we're ready to sketch our new region. So we draw our axes here. We're going to be in the U and V. What do we have? Well, we're told U equals 2. So we'll put a sketch here. U equals 2. And we're told V equals 1. Put a sketch here. That's V equals 1. And we're told V equals U squared. So it's a lot like the Y equals X squared. It's a parabola. So I'm starting and I'm coming up. And terrible picture, but the question is, which part is the right part? And the answer is it's this part, because this is the part that's bordered by all of them. Now, why do I say it's a terrible picture? Well, because this intersection was supposed to be at 1. Well, obviously that picture's off. All right, so there's 1. This is at 2. V squared, this would be at 4. Well, it's a bad picture, but the math is good. Even a bad picture is better than no picture, I suppose, as long as you're getting the right ideas. Now, let's think about our integral. We're ready to make our integral. So we're going to integrate. We'll work on our bounds in our second. 2i dx dy becomes the Jacobian, so that's okay. We don't need to worry about that. We have our function cosine u cubed minus 3u, and then we have either du dv or dv du. Now, looking at our situation, we're not going to have much luck if we integrate with respect to u first, because we're just going to be stuck. So we better not integrate with respect to u first, so let's do dv du. So let's figure out what's happening. Well, what can we say about u? U goes between 1 and 2. So 1 to 2. Where does v go from? Well, v goes from the bottom curve, which is v equals 1, to the top curve, which is v equals u squared. So we're now ready to go. Because the nice thing is, this is an easy integral to do on the first layer. Cosine u cubed minus 3u times v, evaluated from 1 to u squared du, which is the integral 1 to 2 of cosine u cubed minus 3u times the quantity u squared minus 1 du. Now, we should be suspicious because, they expect us to get an answer, so we should say, okay, how does the u squared minus 1 help? Well, in this case, we can make a good substitution. So let's suppose we set our inside equal to our substitution. Now, we already are using the symbol u, so let's double down. W. W equals u cubed minus 3u. Then what would dw be? Well, 3 u squared minus 3, all times du. Notice that's almost u squared minus 1 du. In fact, if we divide both sides by a third, we get 1/3 dw is u squared minus 1 du. So this is the integral, updating cosine of w times 1/3 dw. I'll put the 1/3 in front. Now, where do we evaluate from? Well, from 1 to 2. Plug in 1. We get 1 minus 3. 1 minus 3 is negative 2. Now plug in 2. We're going to get 8 minus 6. Well, that's 2. So negative 2 to 2, 1/3 cosine w. Now notice, cosine w is an even function. What does that mean? Well, it means we can just double and go from 0 to 2. And now we're in the home stretch. Integral of cosine is sine. So this is 2/3 sine of w, evaluated from 0 to 2. And sine of 0 is 0, which means our final answer is 2/3 sine evaluated at 2. And that's it. Done. Good. Now this was actually a fun problem. It came from, as was mentioned, a recent exam. And no part is really hard. It's just a matter of being careful, being methodical. Go through, do the work. If you do the work, it's not too bad. Since we have a little bit more time, one more. All right. Haven't tried this one yet, so hope it works. Let R be the region where you have absolute value of x plus absolute value of y is less than or equal to half pi. Find the integral over the region, cosine x, cosine y, dA. There's even a hint. It says, look, if you take cosine times cosine, this is a product to a sum trig identity. Cosine A, cosine B is half cosine of A plus B plus half cosine A minus B. Well, nothing else, we can apply the hint right away because it's of just the right form. So this is the integral over our region of 1/2 of cosine x plus y plus 1/2 cosine x minus y dA. Now, what's happened? Well, this problem is a little bit different because there aren't any substitutions given to us. So we actually have to come up with our substitution, which suggests it's probably not a hard one. Let's think about what it could be. And so sort of there's a clue. We see some things floating around, like x plus y, x minus y. Well, that's very suggestive that perhaps those should be our substitutions. But let's see if we can't get even more suggestive. All right. What does it mean to say absolute value of x plus absolute value of y is less than or equal to 1/2 pi? If we think about what absolute value of x means, it's like plus or minus. So what you have is you have a couple of possibilities. Plus or minus x plus or minus y is less than or equal to 1/2 pi. Well, maybe that's not the right thing to say. Let's say that the border is plus minus x plus minus y equals 1/2 pi. So there's 4 possible combinations. So let's graph these really quickly. So suppose I did plus plus. X plus y equals 1/2 pi. That would be this line. So here is x plus y equals 1/2 pi. Now if I did minus minus, that would be on the other side. It would be over here. This would be minus x minus y equals 1/2 pi, or probably a better way to write it is x plus y equals negative 1/2 pi. Now what if I mixed? Well, suppose I want to have x minus y equals 1/2 pi. So in other words, plus minus. Plus minus would be this line. So this would be x minus y equals 1/2 pi. And then the last one would be minus plus. So if we do minus plus, we're going to get this line. So this is minus x plus y equals 1/2 pi. Or maybe another way to write it is x minus y equals 1/2 pi. So what are we trying to integrate? Well, our region, it's a diamond. In other words, it's like we took a square and we turned it sideways. All right, so that's where we're trying to integrate over. Now, when we're looking for substitutions to make, you should always look in 2 places. The inside of the function, we said, well, those are x plus y and x minus y, and the boundary curves. You'll notice that on the boundary curves, we consistently have things that look like x plus y or x minus y. Well, okay, so that's suggestive. If we see the same types of functions showing up over and over again, that's the kind of substitution we need. So, we're going to make the following substitution. U is x plus y, v is x minus y. So there's our substitution, our first step. Now let's do our Jacobian. So we do our Jacobian uv, xy is equal to, we're going to say it is u sub x, v sub x, u sub y, v sub y. And that's, all right, u sub x, 1, v sub x, 1. U sub y, 1. V sub y, -1. And take that determinant, it would be -2. But of course, we want the absolute value of that, so we're going to say it's 2. Well, what does this mean? That says that if I have 2 dx dy, that's going to be equal to du dv. Or I could say that dx dy is equal to 1/2 du dv. Now the reason I did the 2 moving across is there's not really a 2 yet. All right. So, what's next? All right. This, by the way, dx dy, why I should also point out, is also called dA. So now I know how to write dA in terms of u and v. And the reason why I needed to switch to u and v is notice that my original functions are in terms of x and y. So dA really starts off as being in terms of x and y, so I need to have a switch to u and v. All right, we're there with the Jacobian. Our function, this is the nice part. We can almost just write it down. In that, we can write it down. So our function is the following. This will become 1/2 cosine u plus 1/2 cosine v. Good. That was quick. That was very quick. Well, because our function guided our substitution. So it really should be quite simple in terms of our final substitution. Now, the last part, the bounds. Well, these should be also quick as well, because we've set it up to be quick. So what do we mean by that? Well, we see that we have here u equals 1/2 pi. Here we have u equals minus 1/2 pi. Over here we have v equals 1/2 pi. And then over here we have v equals minus 1/2 pi. And it looks like, whoops, did we forget our minus there? All right, we have it there now. No one needs to know. I won't tell anybody if you don't tell anybody. So, what do I look like? We look like a square. So we're going from minus 1/2 pi to plus 1/2 pi in the x direction and also in the y direction. So plus 1/2 pi and 1/2 pi. All right. Well, all right. So put it all together, we get that this will become the integral minus 1/2 pi to plus 1/2 pi, and then we get the integral minus 1/2 pi to plus 1/2 pi, 1/2 cosine of u plus 1/2 cosine of v, and then we're going to have 1/2 du dv. All right. Well, our integral is set up. It's set fine, so we'll go ahead and finish it off. If I pull out a half, there's another half, so I can say that this is 1/4. And now we integrate minus 1/2 pi to 1/2 pi. And when we integrate, we're integrating cosine of u plus cosine of v with respect to u. So that becomes sine of u plus u cosine v. And we're going to evaluate from u equals minus pi halves to u equals plus pi halves. And after we integrate, whoops, no, yeah, that's right. Yep. Then evaluate, after we integrate, we do it with dv. All right, well, what do we get? Well, sine of pi halves is 1. Sine of negative pi halves is -1. So when we evaluate, we're going to get 2 here. Then we're going to get pi halves times cosine v minus pi halves times cosine v, which is plus pi cosine v. So that's what we're going to get. Then, of course, we're going to integrate negative pi halves to pi halves. Put a 4th in front, dv. So, what do we get? Well, that's 1/4 times 2v. Integral here, well, that's pi cosine of v. So that is going to become pi sine of v. And now we're going to evaluate from pi halves to negative pi halves. And if we do the evaluation, what will we get? Well, we're going to get 2 times pi halves, which is going to be pi. But then we're also going to subtract 2 times negative pi halves, which is going to be negative pi. So this will simplify to be 2 pi. Well, how about here? Sine of pi halves, that's 1. Sine of negative pi halves is negative 1, so it's going to be pi times 1. Subtract pi times negative 1, which is going to be another 2 pi. 2 pi plus 2 pi is 4 pi times a fourth. Our final answer, simple. It's a piece of pi. All right, good. Now a couple of things to note. You'll notice a few things here, that this is a half, and if you look, it actually is a smaller shape. So there was some shrinking that did occur here. So it's not just a coincidence. Let's see, is it a coincidence? Well, they're not the right shape. There is some shrinking and or enlarging. I'd have to go back and stare at it for a while. But I want to point something out here. What can we think of happening? Well, in some sense, the problem is we wouldn't want to integrate this one if we did vertical slices, because that's terrible, because we switch our bounds halfway through. If we did horizontal slices, that would also be terrible, because we switch our bounds halfway through. But if we did diagonal slicing, that would be great. Well, in essence, once we did our substitution, we've essentially done a rotation. And that rotation allows us to come away and get a diagonal, to turn our diagonal slicing into a vertical slicing. So, substitution helps makes integrals simpler, because you can get your bounds to now work in a cleaner way, line up in a better way. But it's all practice. And the more you practice, the better it gets. So practice some more. See you next time.